In this video, we're going to actually see what the negative numbers look like when we write them into, say, a C program and then compile them into a binary. My goal in this course is to try to show things as practically as possible. It's pretty hard to understand the theoretical stuff without the actual applications of it, so I want to show you what's actually happening inside of programs so that you can see it more in a live scenario. That way you understand why we're really caring about understanding these representations. So I've created a really simple C program. It basically declares some variables. A is equal to -2, B is equal to 5, C is equal to -10. I do some addition with them. I return back the result of that addition. And what I want to see is I want to see what these values end up looking like when we're actually, running the program itself. So what we're going to do is we're going to save this program. I'm going to compile the program. And then I'm going to open the program in GDB, which is just a nice little debugger for us to be able to use, right? So in GDB, we have a layout called ASM, which will show us the assembly code associated with our binary. Now, you don't need to worry about understanding the assembly code yet. We'll get to that eventually. All I really want you to focus on right now is the lines that are associated with the variables, which GDB actually helpfully marks for us. This -2, this 5, and this -10. And you'll see what ends up happening is it's basically moving this data into some location. Again, we don't really worry too much about that detail, but what we're worrying about right now is the values, which are these hashtag values that are shown right here. So we have this hashtag 0x5, 0xFFFF, right? And then FFF6, right? So those are the different values that we have for our program here. Now, in understanding this, basically all you need to know is that if something starts with 0x, it's a hexadecimal value. So that's hexadecimal, right? So then from here, we can intuitively understand the binary associated with each of these values. This -2 value here, this value in hex, right, is a whole bunch of F's. And then at the very end, a value E, right? So let's understand this in a bit of detail, right? So first off, you'll notice that there are a total of 8 hexadecimal values. Each hexadecimal value represents 4 binary values, giving us a total of 32 bits, right? So these are 32-bit values that we're working with. And now the main question that you may have is, what does this look like in binary? Well, every single group of F's becomes a group of 4 ones, right? So we have all of these different ones. And then finally at the end, what we have is the value E. The value E is just 1 away from F, so it is going to be the value 14, which will look like this in binary, right? Now the question is, why is this used to represent -2, right? So in order to understand that, you have to consider what this register or what this data looked like before we took complements of it, right? So let's talk a little bit about that, right? So basically what ends up happening is when this whole thing starts, it's a whole bunch of different zeros, right? I'm not going to write them all out. It's a bit much, right? And then we would have the value 2 stored inside of this particular set of memory, right? Now what happens is, in order to represent a negative number, like I told you, we have to take the 1's complement, which negates everything. It turns everything that was a 0 into a 1 and everything that was a 1 into a 0. So you end up with, a whole bunch of 1's, right? Like I said, and so on and so forth like that. And then the value 2 turns into 1, 1, 0, 1, like this, right? Now for 2's complement, I need to add 1 to this value, right? So what I end up with is, of course, a whole bunch of 1's. And then we end up with 0 carry the 1, 1, 1, 1. And you can see that this ends up being that exact value, right? FFF, FFFE, right? Just like that. So do you see how we got this value by taking the 2's complement of 2 in order to represent it as a negative number? I encourage you to look at this value here and demonstrate it to yourself, right? You should be able to come to this exact same conclusion as me for -10. Basically, the value 6 is, of course, going to be the value 6 in hex, right? So then you would just simply take that 10, apply the 2's complement to it, and see that it ends up equaling this value 6, right? And you'll see that that is the case, that generally this is applying just a 2's complement to this value. And what you'll notice as well is that the value 5 doesn't have a 2's complement applies to it. It just is the value 5, right? Because positive numbers don't need a 2's complement, only the negative numbers need it. So you can see that the negative numbers got a 2's complement and the positive numbers did not. Now, why does this matter? The reason why this matters is because at some point you may be working at a low level. You're doing reverse engineering, you're trying to program an operating system, you're trying to do assembly programming. You may encounter something like this. You need to be able to intuitively understand that this is a 2's complement value, right? If you see something that looks like this, you should first be verifying, is this a negative number, right? Having that understanding is extremely important to actually understanding this program altogether. If you didn't have these comments, which you likely won't if you're doing something like reverse engineering, right? You wouldn't know what these two values necessarily represent. In order to get those values representative, you have to be able to convert them between the different formats, right? You have to be able to understand them as a 2's complement value. So this is the reason why this is important, to be able to intuitively look at a program like this and say, oh, those must be negative numbers, right? And that's not always going to be right. In some cases, they may be large positive numbers, but understanding that they could potentially be negative numbers can help you a lot in understanding, around the context of the program. If in the context a negative number makes sense, then this could be what we are actually seeing or looking for, right? So this gives you some of the intuition around 2's complement. I just wanted to show you that this actually is used in general programming, right? So we could see very clearly here that the 2's complement values are being used, and that's what our compiler gives us when we compile our C code into an actual binary itself. With that, you now understand the basics of signed numbers. What we'll be doing next is moving into floating point numbers and taking a look at IEEE floating point to understand how that is generally represented. So thanks so much for watching this video. I'll see you in the next one.